All right. Knock this thing down. Questions? Everybody's okay. How many have read 1.1 and 1.2? How about 1.1? How about 1.2? And at least look at the examples, right? The idea is again, before this, go ahead and read them up. Just read forward on it. Again, you have to know it perfectly, no, but just give it a good reading. 1.1 and 1.2 in previous editions of the textbook were actually the same section. Because 1.2 is applications. And that's normally how you actually introduce things is you say, here's the ideas behind it, and now here's why we would like to do it for some problems. As far as, again, propositional logic goes, I always say this, you know, everyone should know. And really, considering what the applications are for logic, when I mean everyone, I really do mean everyone. You know, you really, not just people in this class, this is one thing that should be a background for any form of education. So when we get into the idea of logic, reasoning, and applications of such, which is all forms of human discourse. That's what we're doing, right? We're going to form compound propositions. Well, that's talking. And we have all forms of human discourse, and we're going to go through arguments, and we'll talk about what it means to be a mathematical argument, not this idea of getting into an argument and fighting, but an argument of, is this right or not? How do we go through those sorts of discussions? Well, that's everything in terms of sharing knowledge. Actually, what are the three things you guys have to get done before you're even allowed to go into further courses? And if you haven't finished it by your sophomore year, these three topics, it's 4 classes, one of them occurs in 2 sections, all right, that you have to absolutely do. What are your core skills? What are those 3 classes? English, public speaking, math. All right, that's called the trivium. Historically, it says, if you guys are going to learn, you need to be able to think correctly. That's the idea of mathematics. Honestly, discrete should be the core skill course instead of college algebra. Because this really is more along the lines of not only is it college algebra, algebra is a tool for later math courses, right? It's a thing that we use to actually model. Now, on the other hand, this really focuses hard on, do you think correctly? If you can't think correctly, education is pointless. Right? You're just a bunch of emotions running around saying, oh, I feel this way, I'll go do it that way. Why'd you do that? I don't know. Right? Stop, think, how do you model, how do you do? And then how do you actually learn? You have to pick up knowledge through reading and writing. Right? That's the English composition. And this is the other one. How do you share knowledge? Verbally. Probably in the future we ought to add to that. Most people pick up knowledge through not just simply English composition, you know, this whole idea of, you know, asynchronous learning. You have your book, go learn it, right? Synchronized learning, we're talking. But now we kind of have a combination of the two now with like videos and audio, right? You can be asynchronous, go off and learn it by watching and listening. You don't have to necessarily be with me. So there ought to be probably video composition and understanding added to those core skills eventually. Because I think most people here learn any more of their knowledge. How many of you picked up knowledge of history by reading history books or just simply watching movies about it? Right? You're like, well, let's watch it. We tend to, that's how we're starting to learn now. So anyways, everyone should know certain things. And again, what is this table that everybody should know? You should know not P. You should know not Q. You should know P and Q. You should know P or Q. You should know P or Q. You should know P then, if P then Q. And you should know P if and only if Q, right? You should be able to complete this truth table knowing exactly why and what is going on. And if I would take the ordering of true, 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 false, false, true, false, false, and decided to randomly swap them up on you, You should be able to complete this table because you should know why true and true is true, true and false is false, false and true is false, and false is false, right? Doesn't matter the order, right? You should be able to just simply know it. This is your core knowledge. When we talk about applications, we're talking about, do you understand how true and false goes together? If you cannot get this, there's no point in moving on. Just like your core skills for your entire education is English, math, and speech. And if you don't get that done, stop. We will not let you take a class past your sophomore year if you don't have those 3 done. That's how they're starting to enforce that now. Same thing here. If you don't get this, if you don't understand operations, there's no point in moving on. None. So you have to have this, period. You have to understand what logic does, where it makes, what are you doing? It's like, well, I don't know how true and false goes together. All right? Well, I expect you to know that because the rest won't make sense. Along with these things about what you're supposed to know was the idea of order of operations. For compound propositions. In other words, we would just simply mix all those things together, and the order was grouping, followed by negation, followed by and, or, followed by imply, or if, and only if. And so we could say this is level 0, level 1, level 2, level 3, in terms of the level. They talked about precedence, and they put and or. They didn't even do the exclusive or, right, in their little table of precedence. But again, in terms of level, and or and exclusive or are all considered the same level, and so there would always be doubt. Put parentheses, right? These are binary operators. You should only see a single thing to the left and a single thing to the right, whether that thing is grouped in a parenthesis or not, right? Unary, it's unary. It's not one object. So if you're confused, is it not what? Use parentheses to say it's not this. The parentheses group it as these are what the things that I'm talking about, right? All right. So one of the problems that you had to do from last classes, which is always fun when people look at this and they don't work it out, was say 15E, and I'll use my version from 1.1, which is bad English, which would be the following. It is safe to hike, comma, actually I suppose it was to be safe to hike, comma, it is necessary but not sufficient for there to be no ripe berries and you've not seen bears. This is actually an application. It's in 1.1, but this is an application of logic. And so one of the questions was, could you put this in symbolic form? And the book, what I would normally have done on this one is, they did P denotes that you have seen bears. Obviously, that's not an actual English sentence, but in your head, fill out the English sentence. Q denotes it is safe to hike. And then R denoted that you have ripe berries. Right? Now, those are actual sentences, but I'm tightening down just for the sake of time. For myself, I would have probably done B, S, and R. For B for bears, S for safe, R for ripe berries. That's normally what I would have done. And you could have done whatever you want. You could actually, again, and let's say you're going to be programming, and you pick variable names. Picking P, Q, and R would be really dumb variables, right? And actually, since you get to type variable names of any length, I would probably have done seen bears. here, seen underscore bears for the variable, right? And Q, rather than Q, I'd put safe to hike, right? Literally say what the variable means when you're programming. You have plenty of time in a big keyboard, right? In a big giant space. When you read a program, variable choices, pick names that make sense. And when people read it, they should understand exactly what you meant. If you don't do that, life is hard, especially when you debug other people's code. And there's a little hint on picking things, right? For us, why do we use P, Q, and R in one letter? Because we're writing by hand, and you get arm mouse. It's annoying. I don't want to write that. Typing, copy, and paste, you get the freedom to go a lot larger. Anyways, are there words in here that clue you into operations? Okay. Necessary but not sufficient is not a single op, but necessary is what? Necessary is cluing me into there is a what operation here? There's an implication. But what operation is that? There is a conjunction. The word but is an and. Here's some little hints. And can be represented by the English words and, but, yet. When would I pick the words but and yet? Normally you pick the words but and yet when you want to have an emotional emphasis. To say, you know what, the second part I want you to pay attention to. Right? Or is the word or. It's also the word unless. But it's pointing out that under this or, again, this is an emotional emphasis upon the or. Normally what it's trying to talk about is unless this other guy ends up being the dominator of the or. That's normally what you're supposed to do. Like but. You would say, yeah, but pay attention if he's false. Because if he's false, then this entire thing doesn't matter for false wins. When do you use unless? This or this or this or, but who's the dominator of or? True, right? Negation, truth is the or dominator. If it's ever true. It's this or this or this, or if that's true, don't even worry about everybody else. This is true. It's pointing out something that could possibly be true. It needs to stand out. It's still an or, but it tells you to please look closely at what I say next as if it might be a dominator. Under or, is the next guy true? If it's but and yet, is the next guy false? It's still just an and it's still just an or. Anyways, so but, that there is conjunction. That necessary is implication. The sufficient is also an implication. This and is a conjunction. There's the word no, there's the word not. Those are both negations. So I'm going to have, if I just looked at this and I circled those things, how many implications should I see? I better see 2 implications. All right. The implication of the necessary thing, I need to see the implication involving the sufficiency thing. I should see a conjunction with the but. I should see a conjunction with the and. I should see some sort of no. And I also missed one there, that not. That is also a negation. All right. As you solve problems like this, the best way to do things of this nature is to do it in part tools, right? Safe to hike is what? Q. So this is really Q, comma, is necessary and not sufficient, right? I'm putting in some English words here. And not sufficient. Q is involving some sort of necessity and some sort of not sufficiency. All right? Because I say not sufficient, I mean not sufficient. Okay, but what is a necessity thing? What's being necessary? if I left off these words here, but not sufficient for a second, it is necessary for there to be no ripe berries and what is necessary here? Okay, so the necessary thing is the not ripe berries and not seen bears, which would make sense, right? To be safe, it's necessary that you haven't seen bears and ripe berries. That's going to be a necessity. Because if you saw bears, I'm not going to say that's safe. And if you see ripe berries, there's probably bears. So I don't think that's going to be safe either, right? So the thing that is being necessary is that entire bottom paragraph. All right? Ignore the necessity part for a second. What about the sufficiency? It is necessary, right? Ignore the but and the but not, right? To be safe to hike, it is, and I'll just ignore that whole and not, it is sufficient for there to be no ripe berries and not. So who's being sufficient now? The no ripe berries and no, all right? Now, under an implication, the necessity thing goes on which side? If I have an imply, if you have an imply and an object, the right side is the what side? This also has to be known. The thing that is necessary. The thing on the left is the thing that is sufficient. So anything over here is, I have an imply. If you say what is necessary, it goes on the right. If you say what is sufficient, it goes on the left. All right. I needed to keep that. I'll rewrite that here because I need to get rid of my squiggles. Box implies box. This side is necessary. This side is sufficient. And that's just simply a note, right? All right, so this necessary thing is what? All right, I said that the no ripe berries and not seen bears is necessary. So which side of the implication does it go on? Right, the who. And so this altogether becomes Q implies no ripe and no bears. What does the sufficiency thing become? Well, sufficiency talks about the left, so that says that no ripe and no bears sufficient for safe. Don't need that last parenthesis. Is everybody okay that the first one says that the no ripe and no bears is necessary for safety? The other one says that no ripe and no bears is sufficient for safety. Now, if I put that all together, I was saying that it's not sufficient, so all I would do is do what? If that implies is the sufficiency, not sufficiency is not that. Just put a not in front of it. And so all together says that. And again, instead of always using the same grouping symbol, if you break out to new group symbols, it's easier to read. So you would say things like, it is Q implies not R and not P, and it is not true that not R and not P implies Q. Yes?
It says it is necessary and sufficient.
No,
then
then that's the biconditional. Oh. The biconditional is necessary and sufficient is another way of saying biconditional. But this is necessary and not sufficient, which is not the biconditional. It's also say, if I say the words if and only if, that's also the wording for biconditional. So it wasn't literally the wording for biconditional. So does everybody see that I have necessity and not sufficiency for safety compared to not ripe and no bears? And again, a more intelligent way of done this would have been safety implies no ripe berries and no P, right? And you would actually even probably use the entire word. Safe. If I would probably have picked my own labels, if I would have picked my labels, I would have made it look like this. Make it easier to read. Safe implies not ripe and no bears. And it is not true that no ripe and no bears implies safe. It's much easier to read. That'd be a better label choice. And if you look at it, does this make sense? And now if this was a real world application, does that make sense? It's necessary that if you want it to be safe, it better be necessary that you haven't seen bears and there's no ripe berries. Because really what you're saying is there's no food for bears. Well, they might be wanting to eat you, but there's no ripe berries that I've seen and there's no bears, so it's probably safe. By the way, it's not sufficient. Why would it not be sufficient? There could still be a bear, right? Or like there's a cliff. Oh, it's safe to hike that. Well, the trail got crushed by a cliff. You go around the corner, down you go. It wasn't safe. It's the middle of a thunderstorm. It wasn't safe. Right? Is everybody okay with that? Another application of this is if I would take the exact same problem is, now one of the questions I could ask is, could you make a truth table for this? Could you go through this problem and say, all right, this is what I had, and that's my answer, right? You would box that out. Could you make a truth table? So you would have, if I would use the P, Qs, and Rs, right? I would have three variables here, and so I would have P, Q, and R, and you would go true, 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 false, 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 true, true, false, false, true, true, false, false, and then true, false, true, false, true, false, true, false. And I think P is, this is where you pick bad names, right? P was bears, Q is safe, R is ripe. So that would be whether you saw a bear, whether it was safe to hike, and whether there was ripe berries. And so then if you would go through this, and you would make your truth table, and so you would do things like, how would you build out this truth table? I would want things like not R and not P, right? And sometimes you don't have to make the row, don't make the column of not R, because not R is pretty easy. It's not R. Just flip the truth values in your head. And so normally you would do things like, okay, what is not R and not P? And then after you do that one, go ahead and we have two implications. We would have things like, okay, what is Q implies not R and not P. And then we would also have what is not R and not P implies Q, right? And then you would have those two columns. And then the last thing I would do is I would just simply put everything together, which is the compound proposition, right, from above. Do the entire thing, which is one and not the other. So what would be not R and not P? Under and, who dominates? Under and, who dominates? False. So if there's ever a false, the entire thing is false. So what you should do is look for falses. So for example, not R and not P. If I take a not P, the first four rows are what? False. So no matter what, this is going to be false, 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 false because of the not P thing. Now let's focus on not R. What's not R? False, true, false, true, false. Well, I don't care about the first four. They're falses. But look at the bottom four. What would it be? False, true, false, true. So it's definitely going to be a false here and a false here, period. And now comes the question of, all right, what would I have? Not R and not P for false, false would actually be true, true, and so that's a true. And so this one would also be a true. Right? Use the understanding. Don't sit there and go, okay, false and false is false. False and true is false. False and false is false. False and true is false. You could go through that in your head, or you could just use a little bit of, like, let's do big chunks at a time. Use what you understand about the ops. Okay, then we do implication. Q implies. All right, what's false implies anything. True. So if Q is false, that implication is what? True. So wherever is Q false, this has to be true. So this is a true, this is a true, this is a true, this is a true, because they're vacuous, right? And what would be a trivial truth? Well, a trivial truth is if the right-hand side's true, it's true. Well, when's the right-hand side true? Only, say, there, right? Now we could go back and ask, well, what is everything else? Everything else is going to be what is Q, which is this column right here, in this. What is true implies false. False, right? And that's what I expected, right? So I'd have true implies false is false. True implies false is false. True implies false is false. And that's it. What about the sufficiency thing? Well, again, see all those falses? What's false implies anything. So all these falses are vacuously true. So that ends up being, oh, that's a true. True, 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 true. And then we can test the rest of them. What is true? What is that, a Q? What is true implies true. True. And then what is a true implies false? False. And so I would have just simply true and false. This also gives us kind of an interesting thing. This is a contingency, right? It's almost true. The thing that's always true is called a tautology. Anything that's always false is called a contradiction. Anything that's sometimes true, sometimes false is, well, that's contingent. What do I notice? No ripe berries and no bears imply safe is usually true. When's the only time that's false? When I have not R, right, which means that R is false, which means not R is true. In other words, there are no ripe berries, there are no bears, and it's not safe to hike. That's the only time that statement would be false. And then we can finish the rest of this, right? And so what this allows you to do is to turn English into symbols, symbols into truth tables, but the truth tables are more along the lines of, do you understand the operations enough to have a discussion? Somebody said something. They said, well, it's sufficient, right? It's sufficient for there not to be ripe berries and no berries for it to be safe to hike. And you'd say, well, that's usually true, but there's one condition where it's not. And we said, well, it's not sufficient. Well, then what would you do to that entire table? Flip it. Well, it's only true in this condition, right? And then you would have the idea of, well, it's necessary. Well, it's contingent. Sometimes what you just said was false. Sometimes what you said was true. It's false in these conditions, true in these conditions. The idea is to go through those arguments and say, when is this not right? When what they just said, when is it false and when is it true? That's the idea of understanding the operations and turning English to symbols. And the symbols help because they allow you to break it down into concrete examples and then look at it and have a discussion about it. You need to get good enough, though, that you can actually have all of that work and do it all in your head, right? When a person's having a discussion, all of what I have written down should be built in. You need to do it well enough. And again, this just simply models human behavior, right? This is mathematics. It models something that is. If somebody comes up and says, you know what, being safe to hike, it's necessary and not sufficient for you to not see berries and not see bears. It's like, what did they just say? I mean, we start off with game examples like this because what if they start talking about things like that actually involve costs? You're in a business, right? Or actually involve human lives. You're in politics and are going to be making decisions. That involves life and death. You have a finite amount of resources. Where are you going to spend it? You need to be able to get this sort of stuff down and get familiar with it. And that's kind of the first application, so 1.2 is simply applications of propositional logic, right? that first one, in terms of the applications, one of what we just did actually involves kind of three things. One, can you take English and you can put it into symbols? Can I give you symbols? Can you go back into English? And can you put the two together? You know, kind of, I suppose, A, B, and C is the idea of truth tables. But not truth tables just because it's like, this is not arithmetic for the sake of arithmetic. Numbers mean something usually when you model, right? It's like, oh, look, I did math. Well, what did you do math for? Well, I calculated the entire inventory of the clinic and how much money is sitting here in vaccines and drugs. Okay, the numbers actually meant money, right? So there's a reason for it. And for us, truth tables are not truth tables because I want you guys to write a bunch of T's and F's. I ought to put a timeout here. T's and F's, that's a truth table. Zeros and ones, that's a bit table. That is not a truth table. Now, we will cover that bit-based things and truth-based things are very similar and they're tied together, right? They're both under the concepts of a Boolean algebra, which is this greater field of math, right? It talks about you have two objects and these laws apply. By the way, logic has applied it. Bit logic has applied to it, right? So if I see zeros and ones, it's wrong. I ask for a truth table. The other is, please put it in the order that I've been doing it. A lot of people go false, 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 true, 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 because they're used to 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, right? And that's, please put it in this order. Why? Just for the sake of my sanity. Because if I have to grade this, one of the ways that you grade is a snapshot. I see trues and falses, and I look at this, and I expect to see this pattern, and I look at yours, and I don't see that pattern. That doesn't mean you're wrong. That means you have a different pattern. And if you would decide, oh, I'm going to randomly rearrange the rows, let's say only 70 people stick around. Let's say only 50 people stick around in this class, right? 50 people. If I have to take 5 minutes per person per problem, and there's 10 problems on a test, I'm not going to get it done, right? So please stick to patterns so that we can agree upon this. If you don't, I'll just make a note, but don't make zeros and ones especially. You do when I ask for a bit table. It's kind of like just sticking to the, asking, reading the instructions. All right, truth tables. I don't mean just simply constructions of truth tables. Really what I'm talking about is when I have truth tables is can you get to the point of the idea is when true and when false. It's the when that matters to me, and it's the when that should matter to you. Yeah, you might simply say, construct the truth table, you construct the truth table, but you should be thinking about when. Why is this true? Why is this entire line, why is it true on the n-compound proposition? What was true about the first values of the compound variables? Why is it true? Why is it false? Is it always true? Is it true only in one condition and false in all others? Is it always false? You should look at these sorts of things and be able to get through the understanding of looking at a table and asking what's going on. Because not only the table then can help you back on your English component, because this is a model of something. We're doing toy models, so we build up our abilities. But eventually this needs to go into the real world. You use this in real applications, right? Real, true discussions. One of the examples in the book, using these three things, we had particular examples, like one was like above. An example of something like this would be called a system specification. Which everybody does all the time. Right? Constantly, every single day. How do you make the choices for what you do to get to campus? Right? You are flowing through a system. And if you're going to do things like, isn't it great when you have, let's say how many people driving 135? How many live up north? Or and have to go through all that construction. Isn't it great how they decide, we're going to cut off half the road at a particular amount of time? When? Are people going to be able to do it? Well, how about let's take all of the ability to go from this part of Wichita to West Wichita, going up and then on 235 around, let's just completely block that exit. Well, how people are going to move? Because they have to. How are you going to reroute traffic? How much time should you put on a stoplight? Right? System specifications are, as you go through this, wouldn't it be great if a person came up with a system specification and then they started working it out and it ends up being always false, which means nothing works? Which, how many people have coded and done programs where it ends up being, oh, it worked. It's like, and you go look through it and say, everything that you designed ends up being at a deadlock. Right? You have no initialization. You have no axiomatic method where it kicks off the entire process. This will never work. How many people could actually have that argument to go down to what a person says, this is my code and this is my program? Could you look at that well enough to say that, well, this is to this library, it's never going to work. It doesn't do what you say it does. We do this in the toy sense, so eventually we can build up how you think so you can leave this and understand what you're doing. That's why we play games, usually reasonable games, right? Checkers, chess. You build up this ability to analyze, create a system. So system specifications are one. Other classic examples of this are logic puzzles. Logic puzzles are interesting because logic puzzles are getting down to that part right here. Really. Logic puzzles simply say you state all of these sorts of things and ask for, are there deadlocks, what's going on, when would this be true, what would you know? And so classic logic puzzles, say, how many people have heard like the Island and Knights and Knaves? Which is also the truth tellers and liars. Or like the most, the world's most difficult logic puzzle type of thing. Normally we have problems of that where you have three types of things, right? Sometimes they'll talk about, okay, these are, three things that answer questions. 3 machines, 3 gods, 3 people. That's the idea of knights and knaves and normals or spies, right? And so the idea is a knight is a person who always tells the truth. So you have a truth teller. In all combinations, they only tell the truth. And you have knaves, which are also the liars, right? Who, in all conditions, will only tell a lie. They will never tell the truth. And honestly, people who always lie are just as efficient as people who always tell the truth, if you know who they are, right? Because they are telling you, what the output always is because they're always going to lie. It's the third that's always difficult, the normals. Which is, no, I'm going to lie, I'm going to tell the truth. And they have things like, okay, they randomly tell the truth or randomly lie, or they tell the truth or tell a lie given particular conditions. And so that's one of the things they ask is they have 3 people and you got to figure out by asking a certain number of questions. And so one example here, and star problem is difficult, but I don't usually, for some of these are not if you work it out a bit. So we would have this. Each inhabitant of a remote village always tells the truth or always lies. So we're only talking about knights and knaves. We have no normals. A villager will give only a yes or no response to any question you ask. Suppose you are visiting this area and come to a fork in the road. And so I have this nice little example. Over here and over here, we've got, here we have death. Over here we have life. Here we have a person standing here, right? And you come up. Here's you. And you are going to ask one question. And that's it. And your goal, right, is to say, goal is point to direction of life. A little variation of what the problem is. What you want him to do is to point in the direction of life. Now, if he was a truth teller, what would you ask him?
Where's life?
Where's life? And he would point to life, and there you go. You know who he is. He has a nice little label. I always tell the truth. Okay? And then you have a liar. What would you ask him? Where's death? And he would say, well, I can't point to death. I'd lie about that. I'm going to point to life. So he's going to lie about it, and he would point to life. But that's if he had, well, now we got a problem. What name tag would a truth teller put on himself?
Truth teller.
I'm a truth teller. What name tag would a liar put on himself? I'm a truth teller. So everybody goes around with the label, I'm a truth teller. So we don't know. So you come to, oh, look, he's a truth teller. I'm going to ask him which way to go. Well, I don't know. You might be dead if you hit the liar, right? I'm going to ask which way to life. Go that way. He's laughing, right? So you get to ask one question. You can't ask, it was like, well, thanks, well, maybe I should ask him, I see the sky's blue, and I could ask him, is the sky blue? And if he says yes, I know he's a truth teller, and then I would ask him the second question. If he says no, I know he's a liar, so I'd rather ask him which way to death, and he'd point to life. But that's two questions, so I could do it in two, right? I could ask him things about that, a known truth. So if you would ask a known truth that you both agree upon, you could figure out who he was, and then ask the second question. So I can definitely do it in two questions, but I want to do it in one. What do liars do? What mathematical operator do they do?
Negation.
Negation. They always negate. What's a negation of a negation? It's the original, right? So not true, false is false, true, but not that is back to true, false. So if a liar negates once, but a negation of a negation is the same as the original, what does a truth teller do? Nothing, right? A truth teller of a truth would leave it alone. So a truth teller would be true, true stays true, false stays false, true stays true, false stays false. So I'm going to ask you how many. So really what I probably ought to do is ask a question about a question. If I were to ask you which way you would point, type of question. So if I did ask you which way to the road of life, which way would you point? That's a nested question, right? It's actually two in one. I'm getting away because I only said the words, huh? Right? That's how we ask questions. We put a huh at the end. Okay, what would the truth teller do? If you were to ask me which way to the road of life, which way would I point? All right, well, if you did ask me which way to the road of life, I would point to life. Which way are you pointing? That way. I would point to life. Now, what would the liar do? If I were to ask you which way to the road of life, well, if you did, I would point to death. Which way are you pointing? That way. Right? So he has to lie about his lie, which makes him do what? Tell the truth. And so, therefore, it's a nested question. So it's a not event. So I can get by with one because I needed two, so I'm just going to do a question of a question to get by with one question. So I make him lie about his lie. So if anybody just simply does the PDF, it's not going to be fun. Is everybody okay with that? And see, that's what the idea of logic puzzles are. Logic puzzles are knowing enough about the ops and how the operations deal with what you're modeling to try and dig out, different things. And so they have different problems. Like people stand up. We have the knight, knave, and spy. Spies are normals. And the first person standing there says, the third is a knave. The second person says, the first person's a knight. And the third person says, the second person is a knight. So we had three people standing up here, and the first goes, that guy over there, third in line, he's always a liar. The second person says, by the way, the guy who just talked, he always tells the truth. And the third guy says, by the way, this guy always tells the truth. The thing is that what do we have? One knight, one knave, one spy. Who's who? And it's you start to ask questions like, what can people say? For example, who can say, I'm a knight? Okay, A knight would say it because he has to. A knave would say it because he has to. Well, no, he actually has two choices. What can a knave say? I'm a knight or I'm a spy. But he can't say I'm a knave. But what can a spy say? Anything he wants. So if a person says, I'm a knave, who do you know who he is? He's a spy. He's the only one that could ever say that. So you try to use those sorts of events to say, oh wait, he can't do that because they limit out their abilities. So what if all three say, I'm a knight? What have you learned? Nothing, right? They're all allowed to say that, so I have no idea. There has to be some sort of extra information that you're going to be digging out. And so that's understanding the ops as you go through it. And they all get down to, for a lot of them, do you understand that truth table well enough to understand not the fact that you're making T's and F's, but why they're there? What these ops actually do. You can't just simply blow it off. Here's another one. What's the problem with the following? I'm a barber. It's kind of a classic one. I'm a barber. But my rule of not only do I give haircuts, I give shaves. But I will only give a person a shave if they have never shaved themselves. So if you've ever gotten a shave, if you ever went and shaved yourself, no, I have a very exclusive clientele. They're my clientele. So I give haircuts, shave the guys, but for the shaving, I'm the only one who's ever allowed to do it. If anyone else you've ever done it, no, you're not going to do that. So that's pretty easy. We could simply line up all the guys on the face of the planet, and then we would say, okay, who can he shave? First guy, you ever shave? Yeah, no. Have you ever? No, I've never shaved myself. Only I have? Yeah. Okay, you're my client. So it goes and splits the entire world into two groups. Where does he go? He's a guy. So he looks in the mirror. I only shave the people that have never shaved themselves. Therefore, I must give myself a shave. But if I give myself a shave, I shave myself, and I'm not allowed to do that. So which group is he in? If he's in the group that has never shaved, he has to be in the group that he does shave. But if he's in the group he does shave, he shaved himself, and he's not allowed to be in that group, so he has to go to the other. So we have what's called a paradox. Right? This idea of he's in both at the same time. It's that whole true, false, but not both. Okay, this is also another classic example in mathematics of you run into that, skip it. Right? It's one of the things when we get into set theory, we call it naive set theory. We form sets, and if you ever have confusion, just simply say that's a special case. We will pull it off to the side. Maybe someday I'll think about it, but right now it gives me a headache, so I will skip. Right? And that's one of the things that we do. Right? We have to pull, out. Our hope usually is to model things in a generic way and hit everything within classes to say everybody fits in this type, and I solve all of them at the same time. That's not always true. So logic puzzles, as we go through these and kind of like the discussions are, do you understand how the ops work and how they all flow together? So again, you need to be able to take sentences into symbols, symbols into tables, discuss what it's talking about. If I gave you the symbols and told you what the symbols meant, could you go back into sentences? Could you take sentences and write it with, let's say it's an implication. If I gave you things like, for example, safe implies no bear, right? How many ways could you say that? Put this into an English sentence and use the words necessary, sufficient. Use the words if and then. Use the words only if. Use the words unless. Right? Go through that, all those things. Like, can you play around with the particular words and get, parts of it to say, it's just an English sentence, I'm going to say it in a different way. But it all means the same thing. And so that's the main idea of these applications is how the language is interpreted into symbolics, how the symbolics are interpreted within the logic ops, and do you understand how they all fit together? And that's why we have these two sections of just playing around, especially with a big chunk of logic puzzles. This is probably the biggest application for logic, thinking, and thinking long and hard. All right, any questions? All right, that's it.
Hey, wait, are you gonna give us an attendance?